Okay, in this video we're going to complete the trilogy of calculating the integral of the natural log of cosine to some power. So we started off with the natural log of cosine to the first power, then we moved on to the natural log of cosine squared, and now we're going to finish it off with the natural log of cosine cubed. Obviously you could keep going, but I think this is a good place to stop because we see all of the tricks that are involved in such a problem once we get to this point. So previously in this series, we had these following 4 facts that we've used. So the first one is that if we take the integral from 0 to pi over 2 of the natural log of cosine, we get minus pi over 2 natural log of 2. If we do the same thing with the natural log of cosine squared, we get pi over 2 times natural log of 2 squared plus pi cubed over 24. Then next, we used this Fourier series for the natural log of cosine in order to calculate this second integral. And let's just recall that the natural log of cosine was equal to minus natural log of 2 minus the sum from n equals 1 to infinity of minus 1 to the n over n cosine of 2nx. So this looks slightly different than the version that we used in this video. In this video, we had distributed this minus sign through and we had minus 1 to the n plus 1, but it's the same thing. And then finally, we had this fact that we used in the proof of this identity up here, which is the orthogonality of these cosine type functions. In other words, if you take the integral from 0 to pi over 2 of cosine mx times cosine nx, you get pi over 4 delta mn. And let's just recall that delta mn is equal to 1 if m is equal to n, and it's equal to 0 otherwise. Okay, so now let's see how we can do this. So I'm going to open this portal up and we're going to set this equal to the following thing. So we'll have the integral from 0 to pi over 2, and then we're going to replace the natural log of cosine with this guy right here. So that's going to give me minus natural log of 2 minus this sum n equals 1 to infinity of minus 1 to the n over n cosine 2nx, and then all of this is going to be cubed and then dx. So I've just replaced natural log of cosine with this Fourier series expansion, which we calculated that expansion in the previous video. Okay, so now what I want to use is the fact that a binomial cubed has a nice formula. So let's add that in right here just so that we can see it. So notice in this case we're going to have minus a minus b cubed. So my a term is like natural log of 2, my b term is this big sum. But notice that since this is an odd power and both of these are negative, that's the same thing as minus a plus b cubed. But then it's really easy to multiply that out and get minus a cubed plus 3a squared b plus 3ab squared plus b cubed. Great. So that's just a standard binomial expansion. Okay, so that's going to break this thing up into 4 pieces. So let's see. We're going to have a minus out in front of the whole thing. And then we'll have the integral from 0 to pi over 2 of the natural log of 2 cubed. And then I'm going to go ahead and separate these out into 4 integrals. So that'll be the first integral. And then the second integral will be plus 3 times the integral from 0 to pi over 2. And then this term squared times this term. So I'm going to have natural log of 2 squared times this sum n equals 1 to infinity of minus 1 to the n over n cosine 2nx dx. Okay, so I've got that. And then I have plus 3 times this sum this integral from 0 to pi over 2 of the natural log of 2 times the product of this sum squared. So that's going to be n equals 1 to infinity of minus 1 to the n over n cosine of 2nx dx, like that. And then that's going to be squared Good. And then finally, plus this sum, and then finally, plus this integral from 0 to pi over 2 of the cube of this sum. So n equals 0 to infinity of minus 1 to the n over n cosine 2nx, the whole thing cubed dx. Okay, so now we can close this big bracket off, and this is the quantity that we need to calculate. So I'm going to clean up the board, put these 4 integrals in a small as possible space up at the top, and then we'll calculate one at a time. Okay, so I've cleaned everything up so I've made everything as compressed as possible. I've put everything at the top, and this is what we have. So we have our goal integral is going to be equal to negative the sum of these 4 integrals. So we have this first one, which is the integral from 0 to pi over 2 of natural log of 2 cubed dx. So actually, we can go ahead and take care of this one immediately, given that the fact that the natural log of 2 cubed is a constant and we're integrating from 0 to pi over 2. So that's just going to be natural log of 2 cubed times pi over 2. So let's switch that. Okay, so there we replace our first integral with its value, and then we have these remaining 3 integrals where the exponent of the sum is ever increasing. Okay, so now let's go ahead and take care of one of them at a time. So the first one we want to take care of is this one. So the first thing that I want to notice is that this sum inside the integral makes up part of this formula over here. And in fact, notice that we can solve for this sum in terms of the natural log of cosine of x and the natural log of 2. We know what the integral of the natural log of cosine x is, so that'll help us out quite a bit. So I'm going to go ahead and notice that this sum can be solved for. Notice we can just add this to both sides and then subtract the natural log of cosine x to both sides. And this is the same thing as minus natural log of 2 minus natural log of cosine of x. Great. And so what that does is that's going to go ahead and make this integral star equal to the following. So this is going to be 3 natural log of 2 squared. So I'm going to leave all of that out front. And now I have the integral from 0 to pi over 2 of minus natural log of 2 minus natural log of cosine of x dx. Okay, now we can split this into 2 integrals. So notice this is going to be 3 natural log of 2 quantity squared, and then times the quantity 0 to pi over 2 minus natural log of 2 dx minus integral from 0 to pi over 2 of natural log of cosine of x dx. Great. But now we know this is just an integral of a constant over the interval 0 to pi over 2. So this is going to give me minus pi over 2 natural log of 2. Okay, good. And now we're going to subtract from that the integral from 0 to pi over 2 of natural log of cosine of x, but we calculated that previously, so that's going to be minus pi over 2 natural log of 2. So notice all of that is 0. So, in other words, this whole term right here is just going to give us 0. Okay, so given that, I'm going to go ahead and clean up the board, erase that term because we no longer need it, and then push everything else together. Okay, so we just finished arguing that that second integral was 0, so that leaves us with this first integral, which we already calculated down to a number, this third and this fourth integral. So now what I want to notice is I can use this same trick that I did in the last case in order to calculate this second integral. So notice that this guy right here, this sum in here, can be solved for in terms of natural log of cosine of x and natural log of 2. And this is in fact minus natural log of 2 minus natural log of cosine of x, and then that whole thing squared. So that's pretty easy to see. But now notice that we can factor a -1 out of each of these terms and then square them, and that's going to turn this into a plus. So what that means is that that third integral, which is now the second integral because the second integral was 0, is going to be equal to 3 times the natural log of 2. I'll keep that constant, times the integral from 0 to pi over 2 of ln 2 plus ln cosine of x quantity squared. But now we can just use the binomial squaring formula. So we have a plus b squared is a squared plus 2ab plus b squared. So good. And so that's going to turn this thing into 3 natural log of 2 times the quantity. And I'll split this thing up into 3 integrals. So I'm going to have the natural log of 2 squared dx. Then next, I'm going to have twice the natural log of 2 times the integral from 0 to pi over 2 of the natural log of cosine of x dx. So that's the cross terms from the foiling. And then finally, I'm going to have plus the integral from 0 to pi halves of natural log of cosine of x quantity squared dx. Okay, so that's what we get from all of that. But each of these have been calculated in previous videos. So this one was calculated in episode 1 of this saga. This one was calculated in episode 2 of this saga. So, and this one is just a constant, so we're good to go there. So this turns out to be 3 natural log of 2, and then notice here we have pi over 2 times natural log of 2 quantity squared. So that's easy to see because that's a constant, plus 2 ln 2, and then let's see, the integral of natural log of cosine x from 0 to pi over 2 is this guy right here. So it's negative pi halves natural log of 2. Great. And then finally, this integral right here, which is natural log of cosine of x squared. So that's going to be pi halves natural log of 2 quantity squared plus pi cubed over 24. So we get something like that going on. So let's see what we've got going on here. So we've got this stuff that can cancel. So notice here this 2 can cancel with this 2. Now we have pi over 2 natural log of 2 squared, pi over 2 natural log of 2 squared. Those are going to add to pi times natural log of 2 squared. Then we've got pi times natural log of 2 squared here. So those are going to all cancel each other. Then we've got 3 natural log of 2 times that. Well, 3 over 24 is obviously 8. So that's going to give us natural log of 2. Well, actually, let's put it in this order. That's going to give us pi cubed over 8 times natural log of 2. So that means we can replace that second integral with this term. Okay, so I'm going to go ahead and do that, then compress everything up at the top, and then we're ready to look at this third integral. So far, we've simplified the first 3 integrals down to the sum of these 2 terms. So we've got pi over 2 times the natural log of 2 cubed. We've got pi cubed over 8 times the natural log of 2. Now we've got this thing right here. This is the last integral that we need to calculate. So you might think, well, we're just going to do the same thing again. We're going to solve this sum for we're going to solve this equation for this sum, and then we're going to plug it in and use some facts what we know, but that's going to quickly arrive at this goal integral, and everything else is going to cancel, and we're just going to actually end up with this goal integral equals itself. And so that's not going to help at all. So what instead we need to do is tackle this guy on its own. So let's go ahead and say that this is star, and now we're going to have star equals to the following. So I'm going to write this as the integral from 0 to pi over 2, and then we're cubing an infinite sum, and the way you do that is with the Cauchy product formula. So we went over the Cauchy product formula a little bit last time. We went over it even more carefully in my video about the Catalan numbers. So I'll let you guys look at those resources in order to see what we get. But what this is going to turn into is the following. So we're going to have the sum n equals 1 to infinity, and then the sum m equals 1 to n minus 1, and then the sum L equals 1 to m minus 1. And now we've got this term evaluated at some different spots. So it's going to be evaluated at L, and then it's going to be evaluated at m minus L, and then n minus m. And so that's going to give us minus 1 to the L, minus 1 to the m minus L, and then minus 1 to the n minus m over L, m minus L, and then n minus m. And then we're going to have the same thing for the cosines. So we're going to have a cosine of 2lx, cosine of 2m minus lx, and then finally cosine of 2n minus mx dx. So that is what we need to calculate. Okay, so now I'm going to go ahead and move this integral inside the sum, and that's going to allow us to do some simplification. So obviously that only works if you've got absolute convergence, but we do in this case, but that's again something that we're not going to prove. So we have m equals 1 to n minus 1, the sum L equals 1 to m minus 1, and then notice all of this stuff on the top simplifies to minus 1 to the n power. So notice we have this minus m and this plus m cancel, the L and the minus L cancel, so we get that. Then this is going to be all over L, m minus L, and then n minus m. And now we have the integral from 0 to pi halves of cosine of 2lx, cosine of 2 times the quantity m minus lx, and then cosine of 2 times the quantity n minus mx dx. So the next thing that we're going to use is this. So, well, first of all, I'm going to go ahead and call this integral, which is inside the sum, blue star, so that I can do some simplification. And then furthermore, we're going to use this sum angle formula. So let's go ahead and use the fact that the cosine of alpha times the cosine of beta is equal to 1/2 cosine of alpha plus beta plus cosine of alpha minus beta. Okay, good. And what we're going to do is we're going to use that on maybe these two terms right here. So let's see what that gives us. So that means integral star is going to turn into the integral from 0 to pi halves of, I'm going to bring this half out front because I can, the half that comes from this sum to product identity, I should say product to sum identity. And now I'm going to have cosine of alpha plus beta. So notice alpha plus beta is just going to be 2m. So that's going to give me 2mx. And now I'm going to have times this guy right here. So because I'm simplifying these terms using this product to sum identity, they're still going to be distributed onto this cosine of 2n minus m. So that's going to give me cosine of 2n minus m x. Great. And then I have cosine of alpha minus beta. So let's see, alpha minus beta in this case is going to give me plus cosine of 2, and then I have m minus 2l. x, where I've used the fact that cosine is an even function to switch the order like that. And then finally I have, this is cosine of 2 times n minus m x dx. Okay, so that's how all of this got simplified. So now what we can do is we can simplify each of these parts using this guy right here. So notice that we know that this part is going to simplify down to pi over 4 times delta of n minus m comma m. Right? So this entry needs to be equal to this entry, but we can actually simplify that. That means n minus m needs to be equal to m, which is the same thing as n needs to be equal to 2m. Okay, great. So we get that. And now let's see what we get for this part. So this is going to give us pi over 4 times delta of m minus 2l comma n minus m. Okay, good. So we've got something like that going on. But notice that this is exactly the same thing as n minus m equals m minus 2l, which is the same as pi over 4 delta n, comma, let's see, n is going to need to be 2m minus 2l. So 2m minus 2l. So we get something like that. So what that means is that we can go up here and simplify this sum using both of those things that we've just calculated. So I'll clean up the board, I'll bring this up, and then we'll start simplifying that sum. On the previous board, we worked down integral star into this quantity. So we've got this sum from n equals 1 to infinity, m from 1 to n minus 1, l from 1 to m minus 1, minus 1 to the n, over L, m minus L, n minus m, and then we have these two Kronecker deltas. So delta n 2m and delta n 2m minus 2l, and we're actually only going to focus on this one. This one is going to produce a similar quantity. So I'm going to go ahead and star this one in blue. This is the one that we're going to work with. And so if we star this one in blue, notice that this is going to set all of the values for n equal to 0 except when n equals 2m. So that means we can take this sum and we can replace n with 2m everywhere. So that's going to be the sum m equals 1 to infinity. Now the upper bound of that sum is infinity. And then L equals 1 to m minus 1. Now minus 1 to the 2m, that's just going to be 1 because 2m is obviously always going to be even. Then we have L, m minus L, and then finally n is 2m, so we have 2m minus m, so that's just going to be m. Okay, great. Now the next thing that I want to do is notice that this m right here doesn't depend on L, so we can just pull it out, and that's going to give us pi over 8, the sum m equals 1 to infinity of 1 over m, and then the sum L equals 1 to m minus 1 of 1 over L times m minus L. Okay, now the next thing we want to do is a trick from Calculus 2, so we're going to do partial fractions on this term where we are viewing L as the variable. So I'm not going to do the details there, but I'll let you guys check that we get the following. So this outer sum is still the same, so 1 to infinity of 1 over m, and then the inner sum is L equals 1 to m minus 1, and now we have the following quantity. So we have 1 over L times m, And then we have 1 over m times m minus l. So now we can split this up into two parts. So this is going to be pi over 8 times the sum m equals 1 to infinity. And notice I can bring this m out. I get 1 over m squared. And then the sum L equals 1 to m minus 1 of 1 over L. Okay, so that's what we get for that first part. And then the second part, we get something super similar. We're going to get the sum m equals 1 to infinity of 1 over m squared, and then times the sum L equals 1 to m minus 1 of 1 over m minus L. So we get that. Okay, now the next thing that we can do is we can take this sum right here and we can re-index it. So we'll re-index it in the following way. We will send m to m minus l. So notice if m goes to m minus l, then m minus l is going to go to m minus l, which is l, and then the bounds will just swap. So really what we're doing here is just reversing the order of summation. And I should say, instead of starting at 1 and going to m minus 1, we're like going from m minus 1 down to m and then re-indexing. Okay, so this is going to give us pi over 8 times the sum. Well, now both of these are the same, so it's twice the sum m equals 1 to infinity of 1 over m squared. The sum L equals 1 to m minus 1 of 1 over L. But notice that that is going to simplify, so that's going to give us pi over 4. And then the sum m equals 1 to infinity of, well, something over m squared, but that something is actually a well-known number. So whenever you take this partial sum of the harmonic series, that's known as a harmonic number. So this is the m minus first harmonic number. Now, I'm going to introduce a little plot hole into our saga, and that plot hole is the fact that this harmonic number has this sum of these harmonic numbers over m squared have a nice formula. This is equal to pi over 4 times the Riemann zeta function evaluated at 3. So there's a plot hole in our story. Maybe that'll be filled in a future video. Okay, so I'll also say that doing the summation with this second Kronecker delta will give us a very, very similar result, which will allow us to write this whole thing as 3 over 4 times pi times the Riemann zeta function evaluated at 3. Okay, so that means that we can replace this integral with that quantity. So I'll go ahead and do that. So to summarize what we have, our goal integral up here, which is the integral from 0 to pi over 2 of natural log of cosine quantity cubed, is going to be negative of this sum. So we have pi over 2 natural log of 2 cubed, pi cubed over 8 natural log of 2, and then 3 pi over 4 of the Riemann zeta function evaluated at 3. So let's just recall that this Riemann zeta function evaluated at s is defined by the following sum. So it's n equals 1 to infinity of 1 over n to the s. So this like immediately converges if the real part of s is bigger than 1, but it can be analytically continued to almost the entire complex plane. So I'll let you guys look into that if you want to. And then, so the Riemann zeta function evaluated at 3 is the sum of 1 over n cubed. So it's that p series. So you might think that something like that would have a nice closed form, but it doesn't. But what I want to recall is that while we were calculating this part of the sum, which came from this integral down here, we actually got this pi cubed as part of a calculation of the sum of 1, n equals 1 to infinity of 1 over n squared, which is equal to the Riemann zeta function evaluated at 2, which does have a nice closed form of pi squared over 6. Okay. So that finishes this trilogy of videos related to integrals of this type.